Alright, so this is going to be 10.1, the ideal and a simple harmonic motion. Um, so I'm actually covering trigonometric functions in calculus, so it's kind of good to see the overlap. Um, but the book really is bad at explaining this, so um, yeah. So ideal springs and Hooke's law. So everyone is familiar with the spring, I guess. I'm sure everyone's at least touched a spring in their life, or something like that. Um, so let's say x is displacement from how far the spring is stretched or compressed from its natural length. For small displacements, x, the force needed to stretch or compress a string, is directly proportional to the displacement. Hooke's law states that an ideal spring follows the idea that a force applied will settle out at the displacement linearly. So that all seems pretty difficult to understand, but let's just take a spring right here. Hooke states that the force that you push onto the spring and the displacement that you travel is going to be equal. But note that this will be at a settling point. So let's say I apply 10 Newton force, um, and the spring constant is 2.5 newtons meters, um, such that 10 equals 2.5x, and x will be equal to 4. So that means that we should expect the spring to compress 4 meters, such that um, we have a 10 Newton force going this way. But note that this only happens when you let the spring settle out. If you push the 10 Newton force onto here, I'm sure it will go a little bit past 4 meters, but then the restoring force will bring it back. But I guess that's a little bit of an illustration for you. But Hooke's law basically states that um, a force applied is a linear relationship with the displacement traveled for small distances. So this means if you push it to, and because this is a constant, it's basically in the form mx. So basically, I bring it here where k is a spring constant. Remember that force is in the units newtons. Um, so that would be in this units would be um, equal to n divided by m times m. So when these cancel out, you're given newtons back. So it's just simple dimensional analysis there. So essentially, Hooke's law states that the amount of force you apply to a spring is how much the spring will compress um, based on what the spring constant is. So let's say the spring constant is 3 newtons divided by meters, so 3. And let's say that you apply a force of 12 newtons. This means that the spring will go 4 meters backwards. Um, but let's do an interesting thought experiment and let's lower or not a thought experiment, but let's lower the force of the spring constant, or the magnitude of the spring constant, to 2. This means that it will compress 6 meters. Note that a lowered k means that it will compress more, and a higher k, because it's an inverse relationship, will mean that it will compress less. So basically, k is how stiff the spring is, which is what many physicists like to say. A higher k means that more force is required to move to the same displacement, because the force divided by the spring constant will give you the effective distance traveled. So let's move on. The restoring force is pretty simple. Now the book sucks at explaining this because I read the book, and it doesn't really mention that word for word. But essentially, a restoring force, let's say that we push a spring here, because remember that a spring is a conservative force. That's back in chapter 6. And we apply 10 Newton force this way, such that we have a 4 meter displacement. The spring has a restoring force, which is F equals negative kx. The reason we say negative is simply because we are dealing with springs in the one dimension. So this is going to be F restore. So I'll put FR, and we'll say that this is FA, which is for F applied, which is kx, such that the net force is going to be equal to FR plus FA, which is going to be equal to 0, which means that there will be no net displacement. So if you stop this Newton force here, what will happen is that the spring will go back to its original length, or its original unstrained length is what the restoring force means. So restoring force is the spring's natural tendency to return back to its state of unstrained behavior, or its natural natural state, essentially. Newton's law on spring. The spring force is just another force that contributes to the net force. Newton's second law applies here, even with the F. So the summation of kx's for small springs will always equal 0 if there's no net movement. A motion is simple harmonic, which essentially is a pretty hard thing to grasp. But let's say that we move, like let's say this is a piece of paper down here. Let's say we're moving this piece of paper to the right. And this is just going up and down, up and down, up and down. Then as the paper is moving to the right, it's going to be tracing a mark like this, like this, like this, as you can see right here, as the spring moves. So motion is simple harmonic if the motion repeats forever with no friction, air resistance, or non-conservative forces. So yeah, also we have to hope that the atomic structure of the spring stays the same throughout. So amplitude is the distance, maximum distance from equilibrium. So it'll typically be the equilibrium point from when the spring settles out, which is pretty smart because, again, amplitude would be the highest position from the x-axis. Position versus time means that the graph is sinusoidal for simple harmonic motion. It's sine or cosine shaped. So essentially, these are all harmonic classifications. So harmonic, if it's like this, amplitude will be the highest. It'll typically be half the wave. So it'll be like right there. Or essentially, because this would be the unstrained position, so this will be the maximum. So essentially, the relative maximum minus the minima divided by 2, which is what you learn in pre-calc. So the motion is smooth and periodic, which is why we said that the spring can't have air resistance, because if it does, then the spring will eventually settle out. So what happens if gravity stretches the spring first? So let's say that, oh, I don't know where that went. Let's say we have a ceiling here and there's a spring just like that. And let's say we have a ball here. Now, the force applied is gravity, so it would be equal to the mass of the ball. Technically the mass of the spring as well, but if we ignore it as negligible, then it would just be mass times gravity, which is the force of gravity, as you know, is equal to kx. I guess it would be negative kx, but you can say mg equals d0 or kd0, or actually kdi, I guess would be better for denoting initial position. So this will be the new initial position because this is how far the ball will drag the spring down. So let's say that if we did it sideways and the spring was this length, x, but let's say we turn the ceiling somehow upside down and we rotate it 90 degrees, then the spring here will be, the length would be x plus k d0, which is essentially how much the spring is compressing. So yeah, pretty simple stuff there. Shorter springs are stiffer. Yeah, the book is really bad at explaining this, in my opinion. So this one's pretty hard to follow, so I guess you would have to pay some attention here. So let's take a spring here, and let's say that you apply a force here, F. The force is not being applied to one spring, so contrary to intuition, it's not that the entire spring is just constant while the end is getting really compressed. The whole thing is being compressed. And let's denote that compression as a distance of x. That means that distance of x is being spread out throughout the entire spring, or being averaged throughout that entire spring. Each coil is being compressed partially by x here. Then we cut the spring in half. If you know any logic, the force should still be the same. But we know that the displacement was dispersed throughout the entire spring, which means that for one half of the spring, only half of the displacement occurs. So if we apply Hooke's law to this, and we assume that the spring constant stays constant, this is what happens. And remember that the original force is going to be equal to this original spring constant kx. These are not the same things. Although the same force should be the same exact force. So to compensate, the spring constant should be double, such that these cancel out, and F equals Kx. So the shorter spring actually has a spring constant of 2K, which is double here. So that means that if you have the spring constant, or if you have the display, or if you have the spring, um, the spring constant doubles. So shorter springs are tougher, or shorter springs, as mentioned before, have more of a resistance to change. Um, so yeah, that's essentially what that states. So I guess the relationship would be K, 1 over number of coils. So yeah, that one is pretty difficult to understand. The proof is here, like I just said. Start with the full spring. Let's say that the original spring has 10 coils, where the spring constant is X, the applied force is F, and the total displacement is X. By Hooke's law, that spring is compressed by Kx. Now cut the spring in half, the spring becomes two identical 5-coil springs. If that force is still acting, the force is dispersed over the entire spring. But since the displacement is spread across the entire spring, it means each coil has a displacement of X over 2. This means Fx equals Kx over 2, but that's not right because remember that the original force we applied was X. So essentially we have to compensate by having the spring constant be multiplied by 2 because that's the only logical way it will work together. So yeah, that's essentially the 10.1.